Have you ever held a snowflake on your palm and wondered how nature created such perfect six-sided symmetry without a blueprint, without an architect, without any conscious design? Or picked up a quartz crystal and marveled at its flawless geometric faces that seem carved by an invisible mathematical genius? What you're witnessing isn't just beautiful coincidence, it's one of the universe's most profound secrets revealing itself through solid matter. Today, I'm going to show you something that will change how you see every crystal, every diamond, every grain of salt in your kitchen. These aren't just pretty rocks, they're three-dimensional mathematical theorems made manifest, living proof of Emmy Noether's deepest insights about how symmetry shapes reality itself. The truth about why crystals form perfect shapes will shatter everything you thought you knew about how nature organizes itself. The story begins in the atomic realm, where invisible forces follow mathematical laws so precise they would make the greatest human architects weep with envy. Every crystal you've ever seen, from the tiniest salt grain to massive geodes, is built according to rules that Emmy Noether helped us understand through her revolutionary theorem connecting symmetry to conservation. But here's what your chemistry teacher never told you. Crystals don't just happen to be symmetrical. They're symmetrical because the universe demands it, because certain symmetries, once established, become unbreakable laws that govern how atoms arrange themselves in space. Picture an atom as a tiny sphere with specific preferences about how close it wants to be to its neighbors. These preferences aren't random, they're determined by the electromagnetic forces between electron clouds and atomic nuclei. When billions of these atoms come together to form a solid, they face a cosmic optimization problem: how to arrange themselves to minimize the total energy of the system while satisfying the constraints imposed by their size, charge, and quantum mechanical properties. The answer, discovered through eons of atomic trial and error, is to adopt crystalline structures with perfect mathematical symmetry. But why symmetry? Why not random arrangements or chaotic clusters? The answer lies in one of the universe's most fundamental principles: nature abhors waste. In the language of physics, systems naturally evolve toward states of minimum energy, and mathematical symmetry is nature's way of achieving maximum efficiency. When atoms arrange themselves in symmetric patterns, whether cubic, hexagonal, rhombohedral, or any of the other crystalline systems, they create structures where every atom occupies the most energetically favorable position possible. Symmetry isn't just beautiful, it's the mathematical expression of perfection itself. Consider table salt, sodium chloride, which crystallizes in a simple cubic structure. Each sodium atom is surrounded by 6 chlorine atoms, and each chlorine atom is surrounded by 6 sodium atoms, creating a three-dimensional checkerboard pattern that extends throughout the entire crystal. This arrangement isn't arbitrary. It's the only way to pack these particular atoms together while maintaining electrical neutrality and minimizing electrostatic energy. The cubic symmetry emerges naturally from the underlying physics, like a mathematical flower blooming in three-dimensional space. But the story becomes even more remarkable when we examine more complex crystals. Diamond, the hardest natural substance on Earth, owes its incredible properties to its tetrahedral symmetry. Each carbon atom forms 4 bonds arranged in perfect tetrahedral geometry, creating a three-dimensional network of unbreakable strength. The angles between these bonds, exactly 109.5 degrees, aren't chosen arbitrarily. They're determined by the quantum mechanical requirements of carbon's electron orbitals, which themselves reflect deeper symmetries in the wave equations governing atomic behavior. Emmy Noether's theorem tells us that whenever we find symmetry in nature, there must be a corresponding conservation law. In crystals, the spatial symmetries we observe, the perfect faces, the regular angles, the repetitive patterns, reflect the conservation of energy, momentum, and other fundamental quantities during the crystal growth process. Every crystal face that forms, every angle that appears, every internal arrangement of atoms represents the solution to a vast optimization problem governed by conservation laws that Noether first understood. The mathematics of crystal symmetry is breathtaking in its elegance and complexity. Crystallographers have identified exactly 230 different space groups, mathematical descriptions of all the possible ways atoms can be arranged in three-dimensional periodic patterns. These space groups combine rotations, reflections, translations, and other symmetry operations to generate the infinite variety of crystalline structures we observe in nature. Yet despite this diversity, every single crystal structure can be understood as a variation on fundamental symmetry themes established by the laws of physics. Temperature plays a crucial role in determining which symmetry a crystal adopts. As materials cool from their liquid state, atoms lose kinetic energy and become more susceptible to the organizing influence of attractive forces. The symmetry that emerges depends on the delicate balance between thermal motion trying to randomize atomic positions and electromagnetic forces trying to impose order. Different cooling rates can lead to different crystalline phases of the same material, each with its own characteristic symmetry and properties. Phase transitions between different crystal structures provide some of the most dramatic examples of spontaneous symmetry breaking in nature. When water freezes into ice, the random arrangement of molecules in liquid water gives way to the hexagonal symmetry of ice crystals. This transition isn't just a change of state, it's a fundamental reorganization of matter according to mathematical principles. The hexagonal symmetry of ice reflects the geometry of water molecules and the hydrogen bonds that form between them, creating the familiar six-sided structure of snowflakes. Speaking of snowflakes, these ephemeral crystals represent nature's one of the most beautiful demonstrations of how microscopic symmetries manifest on macroscopic scales. As water vapor condenses in the atmosphere, each growing snowflake experiences essentially identical conditions, the same temperature, humidity, and pressure throughout its symmetric structure. Because all six arms of the snowflake experience the same environment, they grow in identical ways, creating the perfect six-fold symmetry we observe. The infinite variety of snowflake patterns emerges from tiny variations in atmospheric conditions, but the underlying hexagonal symmetry remains constant, dictated by the molecular geometry of water itself. Quartz crystals provide another stunning example of how atomic scale symmetries create macroscopic beauty. The silicon and oxygen atoms in quartz arrange themselves in a helical pattern that spirals around a central axis. This spiral symmetry gives quartz its unique properties, including its ability to oscillate at precise frequencies when subjected to electrical stress. The atomic precision of this spiral arrangement is so perfect that quartz crystals are used as timekeeping elements in watches and electronic devices. Their microscopic symmetry translated into macroscopic technological applications. The relationship between crystal symmetry and physical properties is one of the most important connections in material science. The piezoelectric effect, where a mechanical stress generates electrical voltage, occurs only in crystals lacking certain symmetries. The photoelectric effect, crucial for solar panels and digital cameras, depends on the electronic band structure that emerges from crystalline symmetry. Superconducting, the ability of certain materials to conduct electricity without resistance, is intimately connected to the symmetry of the crystal lattice and how it couples to electron pairs. Modern technology increasingly relies on our ability to control and manipulate crystal symmetry. Semiconductor devices like computer processors depend on the controlled introduction of impurities into silicon crystals, breaking the perfect symmetry in precise ways to create the electronic properties needed for digital computation. Liquid crystal displays work by controlling the orientational symmetry of rod-like molecules, switching them between different ordered states to modulate light transmission. Even advanced materials like graphene and carbon nanotubes owe their remarkable properties to their specific crystalline symmetry. The symmetry of crystals also plays a crucial role in determining their optical properties. The way light interacts with crystalline matter, how it's absorbed, reflected, refracted, or scattered, depends on the arrangement of atoms and the electronic structure that emerges from crystalline symmetry. Precious gems owe their colors to trace impurities that break the perfect symmetry of the host crystal in specific ways, creating energy levels that absorb certain wavelengths of light while transmitting others. The brilliant sparkle of a well-cut diamond results from the interplay between the crystal's natural octahedral symmetry and the geometric precision of the faceting process. Biological systems have evolved sophisticated mechanisms for controlling crystal formation and exploiting crystalline symmetries. Mollusk shells grow as controlled crystallization processes, with organic molecules directing the formation of calcium carbonate crystals in specific orientations to create materials that are both strong and tough. Bone tissue incorporates tiny crystals of hydroxyapatite aligned along stress directions, providing structural support optimized by millions of years of evolutionary pressure. Even bacterial magnetosomes, microscopic crystals of magnetite that help certain bacteria navigate using Earth's magnetic field, represent precise control over crystalline symmetry at the nanoscale. The study of crystal defects, departures from perfect symmetry, reveals just how important crystalline order really is. Dislocations, grain boundaries, point defects, and other symmetry-breaking features dramatically alter material properties, often in useful ways. The strength of metals comes largely from the interaction between dislocations and other crystal defects. The semiconducting properties crucial for electronics arise from carefully controlled crystal imperfections. Understanding and controlling these departures from perfect symmetry has become one of the most important frontiers in materials engineering. At the quantum level, the symmetry of crystal lattices create the electronic band structures that determine whether materials are insulators, semiconductors, or metals. The periodic arrangement of atoms creates a periodic potential that shapes how electrons move through the crystal, leading to allowed and forbidden energy bands. The topology of these band structures, a consequence of the underlying crystal symmetry, gives rise to exotic quantum phenomena like topological insulators and Weil semimetals, materials that could revolutionize future electronics and quantum computing technologies. As we push toward ever smaller scales in nanotechnology, our ability to control crystalline symmetry at the atomic level becomes increasingly important. Techniques like molecular beam epitaxy allow us to grow crystals one atomic layer at a time, creating artificial structures with symmetries that don't exist in nature. These designer crystals can have properties tailored for specific applications, from ultra-efficient solar cells to quantum dots for biological imaging. The precision required for these technologies, controlling the position of individual atoms, represents the ultimate expression of our understanding of crystalline symmetry. Looking toward the future, machine learning and artificial intelligence are beginning to accelerate the discovery of new crystalline materials with desired properties. By training algorithms on vast databases of known crystal structures and their properties, researchers can predict new combinations of elements and symmetries that might lead to revolutionary materials. The intersection of crystallography, quantum mechanics, and artificial intelligence promises to unlock crystalline symmetries and properties we haven't yet imagined. Perhaps most remarkably, the study of crystal symmetry has revealed deep connections between condensed matter physics and high-energy particle physics. The same mathematical frameworks used to describe crystalline symmetries also appear in quantum field theories describing fundamental particles and forces. Spontaneous symmetry breaking, first understood in the context of phase transitions in crystals and magnets, became the key to understanding how particles acquire mass through the Higgs mechanism. The universe itself might have undergone crystallization-like phase transitions in its earliest moments, with cosmic symmetry breaking creating the fundamental structure of space, time, and matter. The next time you pick up a crystal, whether it's a grain of salt, a piece of quartz, or a diamond ring, remember that you're holding a three-dimensional mathematical proof, a solid demonstration of how the universe organizes itself according to principles of symmetry and energy minimization that Emmy Noether first helped us understand. Every facet, every angle, every internal arrangement of atoms represents the solution to an optimization problem solved by nature itself using mathematical principles that connect the quantum realm to the macroscopic world we experience. These crystals are nature's way of showing us that the universe isn't random or chaotic, but follows deep mathematical laws that create order, beauty, and functionality on every scale, from atoms to galaxies. In the perfect geometry of crystals, we glimpse the mathematical mind of the cosmos itself, expressing its deepest truths through the language of symmetry made solid.